Okay. I hope you can hear me. Good evening. This evening's presentation is Techniques on Urban Observing. The presenter is Sean Smith. Sean was interested in space and stargazing throughout his life. And in the spring of 2020, 2 years ago, he became a backyard astronomer, viewing mostly from his suburban townhouse balcony. He dove into the Messier catalog with his 4.5-inch and later 10-inch reflector telescope. In an effort to get more out of his urban observing or suburban observing sessions, Sean became driven to figure out how to get the most out of his townhouse balcony. He put his mathematics degree to use to better understand the magnitude and the surface brightness, as well as how to reduce the effects of glare and light noise to see dimmer and dimmer objects. Armed with all these and trial and error, of course, Sean completed the Messier catalog and more. So here is Sean with his techniques to how to do this from his suburban location. Sean, please take it away.
Cool. Thank you very much, Dr. Otsoy. First, I'd like to thank everybody for coming out and joining in so that you guys can be a part of this. And hopefully we have a really good discussion at the end of this and that everybody gets a lot out of this. Like he said, I do the vast majority of my observing from home. You guys can see the picture right here. That is me on my balcony last week, looking for some stuff on the Herschel 2 list, actually in Orion. And so you guys can see some of the light pollution that I'm dealing with here, because there's Betelgeuse right there, there's Orion's belt, the sword, all of that. And yeah, I knew most of my viewing would be from home, so a lot of this was trying to figure out how to get the most out of that. As nice as it is to drive to dark skies, it's not always an option, and it's hard to waste a good clear night just because you're stuck at home. So yeah. Oh, come on. There we go. So yeah, let's kind of got a little bit into that. What we're going to be discussing tonight. Why are we here? It's that most of us live in an urban environment. We are the Denver Astronomical Society. And so, yeah, the gasoline filter, put it in your car and drive out to dark skies isn't really always an option. I mean, I'm a father of a 1-year-old toddler, and that definitely limits how often I can get out. So, yeah, we're here to learn how to have the best sessions that we can, sitting out under the stars from wherever we're viewing from. So when we talk about urban observing, what are we getting into here? I'm talking about viewing through moderate to intense light pollution, a lot of city light being reflected back at us off the sky, as well as nearby lights interfering with our optics and dark adaptation. Like you'll see some photos coming up where that I took off my balcony here, where I have a street light that is literally right outside my balcony. Yeah, and this way too, you guys can kind of get into what is achievable. So here you can see I have you'll see a couple of my astro sketches. I sketch with black paper and white pastels what I see, and this is the Veil Nebula from my balcony here. So when you see these on here, none of them are astrophotography, which will be pretty apparent with some of them. But it's how things look, kind of managing that expectation of how stuff looks through an eyepiece and what you guys can achieve trying to do some of this. And I'm sure many of our observers have done a lot of this and more. So I'm be very curious to see what some of our more experienced observers have to add at the end of this. Whoop. Sticky keys. So what we're going to talk about tonight is kind of the various things on getting the most out of this, making sure that we're seeing the photons that we want to see as through the photons that we don't. as we found out in our pre-discussion and while we were all hanging out before this started, we've got some ham radio operators here, which is cool because I approach a lot of this as a signal to noise kind of thing, right? So there's what you want versus all the background stuff that you don't. So that's kind of the approach I took through this. One of my emphases for my mathematics degree was on information theory, and there's a lot of talk on signal to noise, noisy channels, things like that. That's kind of how I approached a lot of um, what I worked through here. But we're going to talk about things you can do to make sure that the light is getting into your eye, that final reception of whatever your telescope brought in. It needs to actually get to your brain and be perceived, and there's some ways we can help that. Minimizing the way local lights, it's like street lights, your neighbor's porch light, your own garden lights, keep those from getting into our optics. Kind of looking at magnitude and surface brightness a little bit more to better select what targets might be attainable. I'll show you some stuff that I worked out with that. And then what I've figured out, using various filters and things like that, in order to get through that last bit, that sky glow that's out there. So we'll dive right into, let's get our eyes as adapted as possible. As astronomers, we're pretty aware that the wider we can get that pupil to open, the better. However, unlike if we were to go out to, let's say, the club dark site, it's a lot harder to keep your pupil dilated in an urban environment. There's already other lights around. Like I said, I have a street light right there. It's reflecting off my house. In order to keep my viewing eye as dilated as possible when I'm going after more difficult targets from home, I've got to be a little extreme almost in what I use for that. Um, so I've used everything from just while I'm switching eyepieces or going through my case for a filter or whatever, I just kept an eye closed, put a hand over it sometimes. Uh, there's even, you can use more magnification. We'll get a little bit more into that later because it'll create a smaller exit pupil. So if you can't get your eyes to dilate as much, what that does is it means that if you're using too big of an exit pupil, too low of magnification, what what light is coming out of your eyepiece onto your eye might be landing out on, your cornea and not getting all the way back onto your rods and cones. I've even used hoods a lot through that. In the winter, the hood part's pretty easy. You're trying to stay warm, so you've got a hood on most of the time. I'll pull it up and kind of cinch it down, like so I get a little like mini observatory around my face and the eyepiece. That has helped a lot. In the summer, I used to work as a climbing guide. I spent a lot of time in the outdoors. We have these things called sun hoodies. They're super lightweight, but it does have a hood that comes up to protect your head from the sun. They breathe really well, and they work really well out. The darker colored ones work really well out viewing in the summer, so that you're not dying from the fact that it's still 80 degrees at night and can actually still have something to pull up over your eyes and do that. As well as eye patches. Pull the pirate move, you guys. There's the stories that pirates would wear eye patches so that when they went below decks, they could lift it up, still have some night vision because it would be so dark down there. I haven't gone full pirate style, but I have used bandanas, and I'll tie them and just cover my left eye. That's my usual viewing eye, so that I can maintain whatever dark adaptation I can get in a bright environment when I'm switching eyepieces, filters, looking at my star charts and my apps and whatnot. All of those things help keep those eyes open and really kind of like ready to go so that whatever is coming through, I've got that eye open as much as possible in order to, activate as many of the receptors on the back of my eye. And with that, averted vision is obviously a big deal for anybody that hasn't done a lot of it. Even after getting our eyes adapted as much as possible, in the dark, the human eye isn't really that great at looking directly at a dim object. It's best to look just to the side. And trying to get ready for this class, I can't tell you how many articles I read trying to figure out if there was like a consensus on the sweet spot, and everybody was absolutely positive that they had the spot, and none of them agreed. So what I've been using, I have my spot, but I will still kind of look at wherever the target is supposed to be, and I'll kind of gently circle around it where you're not looking directly at it. You're kind of you're looking and focusing on the area to the side of the target or above or below, but still trying to like pay attention and process where it should be. And some stuff comes through that way. There's a whole averted vision scale on how difficult it can be, where once you find it in everything from once you find it in averted vision, you can see it directly all the way to, I think I saw it, maybe occasionally. So it depends on your conditions, and it's really worth practicing. One of the best kind of weeks out I had was I was in the home stretch of finishing the program for the Herschel 400. I knew I was getting into some dark stuff, really dim galaxies. It was galaxy season, so this was about just under a year ago. And I was like, I'm just gonna go out and practice averted vision so that I can do it. And I ended up viewing over 60 objects over 2 nights, finding them all just being like, well, I saw that one. I'm just gonna move on, and just trying to push my averted vision. And it turned into a huge thing, and it's was a big jump in my ability to view some of these faint fuzzies. Another big thing is if you're not using like a tracking mount, like I use a manual, Dobsonian telescope. So what I'll do is I will set my field of view slightly to the west of whatever I'm looking at and just kind of focus on the middle of the screen and let the star field drift through. And it's amazing how like, letting it move to you can actually help bring that in and see some stuff that for where you're viewing from might be kind of very low contrast. Um, Yeah, so that's kind of that last step is making sure that we're protecting our eyes. The next thing we'll get into is we want to keep stray light out of getting into the scope. That's just more noise right there. Um, Even with some of the best paints on the inside of telescopes, there's still going to be some reflection in there, and that light's going to bounce around, and it's either going to get directly in your focuser tube, or it's going to get onto your mirrors, which is then going to get directed into your focuser tubes. If you're using a reflector, it's going to get past the lenses. Either way, we kind of want to limit that as much as possible. So yeah, we're talking about the problem of stray light here. So this is my cheap done in paint graphic here of a reflector telescope where you guys can see the light beams coming in from rather off to the side. So you can imagine the target that you're trying to view is directly to the left, or straight out in front of the scope. But even lights way out to the side, street lights, porch lights, etc., can get into your optical tube, kind of bounce around in there, end up on the mirrors, and end up in the focuser tube. And that's just more noise in the system that's going to reduce our contrast and make it a little bit harder to see that faint fuzzy. Um, so the first one is, a lot of people build their observatories. So this is a contrast photo taken from, or two contrast photos taken from my balcony where I view. So you guys can see over here, I've got quite a few local lights that are all potentially going to reduce the contrast and add noise into my view as I move my scope around. So I just take some very heavy wool blankets and some dark tarps, and I just tie them to the railing here. I've seen people do everything from build something out of PVC pipes, string it up around trees, and then you can buy, Explore Scientific makes a really nice tent that I've looked at. If I wasn't using a Dob that was low to the ground, I probably would have got it. It would work a lot better if I still had a telescope on a tripod. Um, but yeah, it's just a little bit, and you cuts that down. You guys can see with the reflection over here just how much that kind of reduces how much light gets into where my scope tends to stay. And on more serious nights, I actually have another blanket and I extend it even farther down along here. But this was just going to be a quicker session. I wasn't staying out very long. And then for those who can and have a full yard, maybe, or whatever, there are the full domes that you guys can get and buy. And I've seen on Facebook groups people that build the roll-off sheds, roll-off roof sheds, and all of that. I know I always get jealous because it looks super nice. And all of this will also help your dark adaptation as well. So yeah, domes, tents, improvise. I use thick wool blankets and dark tarps. These also help with wind a lot. If there's a little bit of a breeze, it keeps my scope from shaking around, makes everything a little easier to see. And yeah, it's pretty nice. The next thing, and these helped, I've only done the dew shield, and I've been researching the second part, adding flocking material. As you guys can see, I put a dew shield out on the end of my scope, even when I'm not worried about any of my optics doing. What that does is it extends the tube so that lights more off to the side don't have as much of an effect on getting into the tube and bouncing around inside. They were reducing that. Um, the first time I threw that on to test this theory, I went after a globular cluster in a fuchsius that had been thwarting me time and time again. It was sitting pretty low. It was to the south, which is the worst direction for me to view, because I have a rail yard directly to the south that just has all these bright LED lights that definitely, I actually think some of them are aimed directly up for some reason. It's super bright over there. I've got a very bright light dome. It's probably a full magnitude, if not more, brighter sky in that direction. But I went for it. I threw the dew shield on, put it out there, and this object that had been thwarting me for probably a good month and a half, which was instantly directly visible right where it was supposed to be. Very nice. Yeah. So I was sold pretty quickly on that. The next step is using flocking, which is it's a material. What I've looked up is it's like a very tightly woven felt. It doesn't allow any of the, or it doesn't have a lot in. How do I want to put this? The threads don't come off as easily as some other fabrics, so it shouldn't end up on your mirrors and things like that. But you can actually attach it to the inside of your scope. I was reading articles where people put it inside their focuser tube even, so that any of that, if you're using a dew shield even, any of that light that's more directly out in front that you don't want getting into your scope does make it in there. If it touches the sides at all, it tends to just get absorbed. Things like that. There's like usually sticky backing on there. Um, and for the most part, from what I've looked at, is people usually just do the first like foot or two on that and just kind of cover the inside of their scope. And people say it makes a significant increase in contrast. It's what I look forward to adding that little modification to the scope. And that's actually why one of the nice things is for anybody that's using a truss tube scope with like a really good shroud, your shroud probably acts like flocking as well. So it'll prevent some of that light from bouncing around in there. And if you're already viewing from bright skies, then every one of those little things you can do to create just a little bit more contrast seems to go a long way. So those are the things I've done to make the changes to my scope. Here's a diagram of what I was talking about. So you guys can see the first graphic that we had up earlier, and then again my done in MS Paint same telescope, but now has a dew shield on the front, and then we're going to assume it's got some flocking in there. And you guys can see the same light beams are now blocked. They don't end up in the scope, so there's less excess light in there. Even if it's reduced, it still goes a long way in making sure that whatever light we're getting into our optical tubes is only what we want. So it's gonna. These have actually been surprisingly significant changes. Just the dew shield, and my dew shield actually has some flocking on the inside, so that helps things even more. But yeah, the increase in contrast was striking. I was sold right off the bat. Next, a guy that I chat with all the time, pretty much messaged him right away and was like, "Go buy a dew shield," because he was waiting for me to let him know how it worked. And yeah, the changes were pretty significant. So if you're like me, where you do have a lot of local lights, this does go pretty far. So yeah, the next bit is kind of what everybody really thinks of when they think about viewing from an urban environment. That's sky glow. So this is again, I think this is a 2-minute exposure I did with my phone because I have a astrophotography setting on my Google phone. Again, right here from my balcony. So there's the Pleiades right there, if you guys can see that one. And so even though the app brought a lot more stars than could be seen with the naked eye, um, way deeper than my naked eye limiting magnitude here, you guys can still see this giant light dome. So like directly underneath here, is where downtown Denver would sit for me. Um, so yeah, this is what a lot of us are worried about and trying to think about getting through. And the biggest way to do that, um, most people talk about filters, but by the same token, we want to make sure that we're understanding what we're getting into, really understanding the challenge. So, knowing the type of noise that we're dealing with in our signal. And that gets into the Bortle scale. So many people know, you hear a lot of talk about, Bortle 1 is just like incredible dark skies. You know, can see everything. It's what all of us dream about getting to. Um, to what most of us are dealing with is generally considered Bortle 6 or up. So bright suburban skies to city skies. And that has kind of a corresponding SQM or sky quality measurement or meter. A good way to look that up, I really like this website listed here, the lightpollutionmap.info. You can enter your location and it kind of gives you this map here so you can see pretty much like, you know, black, gray, blue, light blue. That's all pretty good. Downtown Denver is definitely white all the way out to red, yellow. You can see Greeley, Fort Collins, etc. here. But this is kind of the general area that we're working with. Um, I'm on this edge of where it goes from like white to reddish orange over here. Um, and so you can hit this button here when you get onto the website, and you can do it on your phone too, and it'll GPS you, and you can figure out your spot at that time, kind of like what your average SQM is. So I use a lot of that when I'm trying to figure out, and what we'll get into next, on just how rough it is. By the same token, like a full moon night, I've seen a range, but the consensus I've seen looking it up is about a sky quality of 18. Um, MPSAS, I think. I can never remember the exact order of those, but it's the same kind of measurement that we would use for surface brightness of an object. So if you figure that out, that can actually help you in a lot of ways figure out, when you look up an object that you're hoping to see that night, do you actually want to go after it? Do you think it's attainable from your skies? Because I know a big reason I got into really researching this was I spent many nights hunting targets that I had zero chance of seeing with the knowledge I had at the time. Um, didn't know, especially when I didn't own any filters, just not understanding surface brightness and going after things and being a very frustrated backyard astronomer because I wasn't seeing what I wanted to see, and you'd see that it's a magnitude whatever, and then it wouldn't be there, but then you could see a lower magnitude. So trying to make sense of all of that. And that gets into our sky quality measurement versus magnitude and surface brightness. So I pulled a data sheet off the website Telescopius, and for the Pinwheel Galaxy M101, right? Because this is a classic example. This was actually my early nemesis. I can't tell you how many times I tried to find this. I'm pretty sure I could have done the star hop off of Mizar and Alcor to get to it in my sleep. Like my first, especially that 4.5 telescope I had slow motion controls, and I'm pretty sure I could have just done it via muscle memory at that point. So you guys can see it's got a magnitude of 7.9. That's not too bad, right? That seems fairly bright. But its surface brightness, and this is in a measurement of average per arc minute, which is always going to be a little lower. SQM I always find is always in arc seconds, which is going to be a little higher, but there's a nice way to kind of just go from one to the other. And that is, if you have it in arc minutes, if it's this lower one, you just add 8.9. And it'll give it to you in the same units as what you'll get your sky quality measurement in if you use that light pollution map. So your magnitude of an extended object, so nebula, globular clusters, open clusters if they have all this data, and galaxies, the magnitude will always overestimate the chance of you seeing it because it takes the amount of light coming off the entire object and goes, well, what if we shrank it down to the size of a star? How bright would that star be? Well, it's not. It's been all spread out in various different ways. So it's going to overestimate your chances of seeing it. Whereas your surface brightness is the average spread out across that, and there's a formula to go straight from magnitude to surface brightness given the size, the angular size of the object on the sky. Um, and so that's if you all that light was spread out evenly. So extended objects like galaxies will have dimmer sections and brighter sections, same thing with nebula. And so your surface brightness is going to underestimate your chances of seeing it. But generally, in a telescope, you can see about 3 magnitudes of surface brightness past your sky quality measurement. So when I looked up the average sky quality measurement for the Chamberlain Observatory, where the Denver Astronomical Society does its open houses, that has a sky quality of 18.6. So you can generally see down to like 20, something with a surface brightness of 21.6. But again, that's an underestimate. That's going to be the pessimistic way of looking at it. So the two of these things can be kind of confusing and frustrating for a lot of people. They definitely were for me, and I was getting frustrated. And then I remembered, wait, I have a degree in applied mathematics. I can do this. And I also had a lot of time on my hands. So I came up with a way to put it all together and give us a rough visibility index. Given its magnitude, its surface brightness, and the skies I'm viewing from, can I come up with like a measure of difficulty that I can use as kind of a metric to do that? And it works very similar to magnitude and surface brightness, where if it's a bigger number, that means it's dimmer, right? And that formula is what you see here in blue. I apologize to anybody that is math phobic. I don't know how many eyes I just had glaze over on me. I'm sorry. I'll try and move on as fast as possible. But what it is it's the square root of the magnitude times the surface brightness. And you multiply that by the surface brightness divided by the sky quality plus 3. So that's that, like, what's that plus 3 measurement that we were talking about earlier. And then what this is you would raise this second portion here, the surface brightness sky quality measure, to an exponent of 2.5 times the log of the difference between the surface brightness and the magnitude. So I mentioned there's a formula to just get surface brightness from magnitude off of how big the object is. So if you didn't know the angular size of the object, you could actually plug that straight in here, because when you do this, the surface brightness minus the magnitude, it actually reduces down to just how big is the object. So what that does is essentially the larger the object, the more the surface brightness matters in our ability to see it. And so the formula will actually start to favor the right-hand side of this as opposed to this side. So a smaller object like a small planetary nebula, this will be a pretty small factor and it'll favor more this side and things like that. I've been using this for probably well over a year now. I don't know when I actually came down to this one, working out all the different pieces. And this whole thing started because I read an astronomy article on, like, why can't I see these galaxies I'm looking for? And somebody mentioned that he had a buddy that had a measurement that was magnitude times surface brightness. And I started using that and started playing with it. And again, I can get into the math on how I got all of this if anybody actually wants to hear it, but I'm assuming most don't, because most people didn't enjoy math classes. Astronomers, maybe we do. I'd be more than happy to talk about it, but I could also talk about this all day, just like our ham radio operators mentioned they could talk for hours. It's not perfect, but it does give a pretty good ballpark. It is super reliable for me. I've been very rarely led astray where an object with a very large number wasn't actually a very difficult one, or it would say something would be attainable and it wasn't. It was always the stuff that's right there on the line, which you've always got to keep in mind too. You're only as good as the data you bring in, and I've definitely found, you can look stuff up and you'll get a range of magnitudes and surface brightnesses. So, if you have a formula, garbage in equals garbage out. So it's more like a guideline. These aren't really rules. Yeah. So what I wanted to show you guys is, since a lot of people use the Messier catalog, I have it plugged in over here. So you have my visibility index, the magnitude, and the surface brightness in arc seconds. So when I showed you that data sheet earlier, I have already added that 8.9 on here. So if we sorted this, and I have the sky quality set to the Chamberlain Observatory, if I sorted by magnitude, it rearranges the list as such, right? So Pleiades is still up there, but you guys can see there's some stuff that kind of jumps up here that anybody that's done the Messier catalog or is currently working through it knows. The Great Nebula in Orion is a very nice bright object, um, but may not be easier than some of these others to see in a telescope as well. You guys can also see the Triangulum Galaxy up here is definitely not easier to see in a telescope than the Hercules Globular, especially from light polluted skies, right? We could do the same thing and we could sort our range by surface brightness. And we're going to get an entirely different list, right? Now the Eagle Nebula is the easiest up here, and the Pleiades is dropped, but the Pleiades is super easy. It's a big naked eye object even underneath fairly bright skies. So now you guys can see that if we sort again by our visibility index, we get an entirely different list yet again. So the Pleiades jumps to the top of the list, and you guys can see the kind of the big one that I use a lot on this. Where did Triangulum go? Southern Pinwheel's down here. Oh, yep, the Triangulum Galaxy drops all the way down to 82. So that one definitely changes pretty drastically based on the skies that you're viewing from. And then my nemesis, the Pinwheel Galaxy, I should have known, ends up all the way at the bottom. So we can see now that if we jump all the way up and go to our dark sky site, you guys can see these change again. And some of these kind of move around a little bit if I resort it here. So yeah, you can see these guys jump around. Triangulum now jumps up to number 70. And a couple of these kind of jump around quite a bit. I think even, yep, no, Pinwheel still stays down at the bottom, but it now, 12.12 is actually fairly attainable. In my 10-inch, the number that I tend to use as where I start to assume things are going to be pretty difficult and need at least averted vision, if not pretty much know it's not going to be there, is going to be down here in the high 14s, low 15s. So viewing from the Chamberlain Observatory, I would go after the Sunflower Galaxy, M63. I've never pronounced that properly, I think, so I'm just going to say M43. I might try for something like the Spindle Galaxy, M102, just to see how that goes and kind of get a bearing for how things are going. But this is just kind of a good rough index. Helps me plan my sessions to get out there and go after a good number of targets from my balcony because I kind of start with what I'm going to skip and look at and then be like, yeah, no, that's not happening. So, yeah. Let me get back onto. Sweet. Yep. So there's that. What a lot of people use to kind of get through the light pollution right away is Aperture. So just throwing a lot more Aperture at it does mean more light, also means sucking in the same light that you're trying to avoid. Some say that it may not be as helpful with diffuse objects, but will reveal dimmer stars. More aperture does mean a brighter image at the same magnification as something with a smaller aperture. And filters do have a more pronounced effect. Again, I went through a lot of message boards and articles trying to get a little bit more to say on the matter, and people went back and forth. Some said that it didn't work, some said it did. Anecdotally, it seems like everybody who throws more aperture at a bright sky seems to see more. So if you can afford a scope with a bigger aperture, go for it. But I mean, we all make the best of what we've got. They say the best telescope is the one you use. I'm definitely not going to try and set up like a 24-inch on my tiny little balcony because I'm not going to be able to use it because I won't be able to turn it. Um, there we go. One thing I've definitely found looking through more light polluted skies is to use more magnification. It does dim the object overall, but it does make it appear bigger. Um, and that just means that more of the receivers in your eye pick it up, and then your brain kind of decides, well, more of our sensors are saying that it's there, so your brain's gonna actually process it and tell you that it's there. Um, so I use way higher magnification here at home than I would if I was out at one of the dark sites, either, Jackson Lake I go to or the Edmund Klein dark site. But that gets into filters, and this is kind of like our main weapon against light pollution. Um, if only light pollution filters were actually the magic bullets that we all hope and wish that they were. You throw it on, and then it would just might as well be like you were at a dark sky site. But it just reduces a percentage of what's up there. Um, so I have and what they do is they cut out or reduce specific bandwidths of light, and hopefully that those bandwidths apply more to what you're trying to not see than what you are. So yeah, we want to dim the background light more than that we dim the object that we're trying to see. And this definitely works for certain objects more than others based on the wavelength of light that they are emitting in based on the nature of the object. So this is the bandpass filter for one of my go-tos all the time. It's the Bader Moon and Sky Glow filter. So you can see what it does and doesn't let through. So it cuts out a lot of these bands here and these here, a lot of this stuff up here, and then down in the like purples and blues. Um, and it's a pretty good filter. I actually really enjoy using that one. So yeah, our filters versus light pollution. So on the right here, we have the passband for the Orion Ultra Block filter, which is a great nebula filter, where it lets through hydrogen beta and oxygen 3. You'll get, which is, the specific wavelengths. You'll see this is either 500 or 5,000. Doesn't let through any of the H alpha up here in the red, but a good UHC filter actually will let some of those through. And I think that having one of those, even though our eyes aren't made to see the red as well, um, it I think sometimes every photon counts when you're already dealing with some bright skies, so try and get them. On the left here, we have a graph where it's the same idea, but this is what most light pollution is made of. So the black line are kind of the old lights that if you guys look outside, you're going to see a lot more of the oranges, the yellows, and things like that. Those are these guys in this like 550 to 600 range over here, this similar band, a little bit over here. And then the blue line is the new bane, which are the LED lights. They tend to cover the range a little bit more evenly. They're harder to filter out. So they definitely are making things a little bit more difficult for us. And we can get in. It's a whole different topic about having them properly shielded to reduce light pollution and all of that. The Astronomical League has, well, a whole thing on being a dark sky advocate that's definitely worth looking up. So the big question is, will the filter help at all? Like, can you just throw a filter on and suddenly everything's better? Well, as nice as that would be, not really. You'll hear a lot of filters being referred to as nebula filters. So what we have here is the same kind of wavelength spectrum of how bright for the object this object is glowing in the different wavelengths. So you have this huge spike here that's ionized oxygen, as is that one. This is hydrogen beta, and then we have hydrogen alpha over here. So a lot of emission nebulas, not so much reflection nebulas, and especially planetary nebulas like this is. This is NGC 1501, which is a planetary nebula, will have these like sharp spikes. And I pulled this off of, there's a website that you can just Google planetary nebula spectrum, and you'll find a ton of these because these are a little easier to get spectra on. And this is why planetary nebulas respond pretty well to filter usage. And that's if you're doing the planetary nebula program, observing program, a big part of your notes need to be how well it responds to different ones. So emission nebulas may have a larger spike over here on the hydrogen side, which can be a little bit more difficult for the eye to see, but it's still worth throwing a filter on. I mean, you give it a shot and go for it. Yeah, so emission to planetary nebula, it's usually safe to use either a line, so like when you buy a filter and says it just lets through oxygen 3, that's a big one, using for visual observing, or various narrow band filters like um, with the various UHC filters, as well as ultra high contrast filters, which will sometimes let that hydrogen alpha through, or the Orion ultra block. I use both. Reflection nebulas or galaxies can be a lot trickier. I installed a filter wheel on my telescope so I can just click through them, and because it always never hurts to give them a shot. But there's this website here, nedipac.caltech.edu. If you guys wanted to use that, that has for a lot of galaxies their spectra on that. And I use that in kind of a debate I got into with somebody on cloudy nights, that talking about filter usage on galaxies. I pulled for everyone that had spectra done in the observable range. I did 384 galaxies to kind of figure out how well they work. And yeah, that website's right here. You guys wanted to see it. So what you can do, I'll go to one of my favorites here. Type in M77. Usually takes a minute to think. Search in progress. Just to build a little tension here. And then it'll have this spectra tab. Click on that guy. And then on the right, you'll see band. I scroll down to optical. And then if it doesn't need to be, but if it's one of these integrated drift scan, that means that they scan the entire object. It's a little bit more total. Whereas like this one here just looked at this center band. But if we click on this guy right here, you can see this is a galaxy that has those same emission spikes. I mean, these aren't sitting close to 0 like the planetary nebula, but you guys do get these spikes here. And so you can see this over here. This is the range for hydrogen alpha. And then you have our oxygen 3, are these two spikes here, and a little bit of hydrogen beta right there. Those definitely do help quite a bit. M77 is very dim from my home skies, but I throw a filter on and that center circle there definitely pops. So we can go through talking about galaxies, because here's another one for the Rosette Nebula. This is an emission nebula, as you can see, it's pretty strong in that H alpha and the oxygen 3. This one was pretty difficult from my home skies, but with a filter, it was, with averted vision, visible. So it comes out, knowing this and looking this stuff up can definitely help. So when we get into galaxies, kind of some rough things that I have found out. Top are graphs that I pulled from the website I just showed you guys. Bottom is averages of that type of galaxy from that statistical analysis that I told you guys about, where I kind of balanced it through. So you guys can see this is pretty much what most elliptical galaxies look like. You're not going to see too much in terms of any strong emission. So any filter here, I'll try like the light pollution filter, my sky glow filter, but I'm not going to I'm not going to try too hard and start going into the more restrictive filters with an elliptical galaxy. You can see on the bottom, no big spikes. Irregular galaxies, however, tend to be pretty reliable on using either a UHC or, a pretty strong narrowband filter. So this is NGC 3239. Came out pretty strong. You guys can see those pretty good strong spikes. And then this is an average of all the irregular galaxies that I had on my list. So you guys can see that on average, they have some pretty decent spikes. Barnard's Galaxy, which is on the Caldwell list, is one. It's in Sagittarius, and it stays pretty low, so it's actually pretty difficult from where I view. Again, entirely invisible without them, but with a UHC filter that let the H alpha through, it was directly visible. So Yeah, peculiar galaxies as well. Anything that's on the ARP list tends to have a little bit that shows through. So like NGC 3310 was the first one that kind of started all of this because I could see it, but with a filter you could actually start to see spiral structure. I've seen spiral structure in M51, including that little connector piece across with filters that I couldn't see without them. Spiral galaxies are hit or miss. It kind of depends on what they're going through at the time that the light from them is getting to Earth. Edge-on don't show much. There's a lot of gas that tends to do that. Face-on spirals may benefit from a UHC. So here's M77 again. And then there's even some anecdotal evidence of using a light blue 82A filter to bring out some of the spiral features. So you might actually see a little bit more from that. And a lot of this does come down to, galaxies, the irregulars, the peculiars, and some of the spirals have some gravitational effects going on that may be spurring on star formation. Hot young blue stars might
Sean,
make
excuse
up.
me.
What's up?
Excuse me, Sean. Can we ask everybody to mute, please?
Yes. Anybody that is currently on, can you make sure that you guys are muted?
Somebody is making tea or coffee. Please mute yourself.
It's Digby. He needs to mute.
Okay. Thank you.
Cool.
Please
Thanks.
proceed, Sean.
See, I used to teach a lot of classes outside in the outdoor environment. I'm just used to extraneous noise. So, cool. Yeah, so you guys can see it sometimes may not hurt knowing what type of object you're going into. I grew up the G.I. Joe generation, so knowledge is power. And heading after more difficult targets, I will definitely do a bit more research on them to see what edges I can get to work through a lot of this stuff. A lot of the stuff that makes viewing from home difficult. Open clusters like Nebula may not have available magnitude or surface brightness data. If you really want to look stuff up, if you're going to start trying to go after something that might be difficult, I've used Stellarium, looked up the object, same thing with Sky Safari, and clicked on like individual stars in the cluster and checked their magnitudes against with what I expect to see with my equipment. I have also had luck with using blue, yellow, and orange color filters to bring out different levels and layers. So on my sketch of the double cluster here, if you have those different filters and say a filter wheel and you can click back and forth through them, watching the layers change, they definitely bring some more out that you may not be able to see otherwise. Very gorgeous, especially with those different colors coming through. Globular clusters, I've had a range of success with them. If they're already nice and bright and you're resolving stars in them, like on this one, I have my sketch here of M5. This sketch is a composite. I clicked through a couple different filters to bring out different layers and kind of sketched them with different pastel pencils, various grayscale ones in order to kind of get that look there. And really brought it out and showed a bunch of different effects so that I could see, some knots, some different layers, some different tidal tails that are features of the globular clusters. Made the whole experience a lot more enjoyable looking at it. And then doing the same thing at a dark site is mind-blowing. I spent a lot of time staring at a glob at a dark site and clicking through different filters on it. So yeah, when to go after a difficult object, both in time and season. We're dealing with a lot of atmospheric effects when we're viewing from our home skies, our brighter skies. And I will look up some of the ones that are at the ends of the observing programs and have been difficult so far, kind of figure out what's the best time. When is it highest in the sky during a new moon? And I have notes where it's like, try to get it at, 8:50 p.m. on this date, so we want to get it as far away from the horizon as possible because any of the light that's bouncing around and making our lives difficult, that will be more significant closer to the horizon. There's more atmosphere to bounce light and reflect light towards us, as well as we were more likely to be getting closer to the city lights that we don't want to be seeing. We want to see the objects that we are setting up our telescopes to see. So trying to find that and doing some research and trying to plan ahead time-wise can definitely get into giving us a little bit more of an edge on all of that. So yeah, that is the end of my spiel, and we can get into some Q&A here. I know I went a little over, but yeah, I will get back to this, and hopefully we can get into some really good Q&A, because this is usually the fun part of any level of teaching. So
Thank you, Sean.
thank you.
First of all, are there any questions from the viewers here, or maybe I'll go and start with the ones that are in the chat. Bill Smith is asking, says whether the SQM versus magnitude slide available on a smartphone app.
Are we talking about, let's see if I can get back into this one?
Bill,
If this one is, it might be best to screenshot it. I don't know of any apps that have it in there.
Bill, you want to ask the question in more detail? Oh, no microphone, he says. Okay, I guess this is it. This is the thing he's asking. And you are saying it is not available, is it?
Not that I'm aware of. I mean, this is a formula that I came up with here, so I don't know if anybody else has stolen it yet. I've given it out quite a bit, but
is the logarithm 10 based, or
yes, it's base 10.
Base 10. Okay.
Sorry, the mathematician in me would have noted otherwise, and I forget that most. So yes, that's the base 10 logarithm.
Okay. Now we have Pam. Please unmute yourself and ask your question.
All right.
Can we get a copy of
Yes,
the
Jeff.
PowerPoint? This is her husband sitting beside her, by the way. But can we get a copy of the PowerPoint so we can get the equations and all the websites and whatnot without having to try to take screenshots and read it?
Yeah.
I guess you can send me the PowerPoint.
Okay.
And I can send it to. Do send me a message, and I will send whoever sends me a message. I will forward it to. Okay. So that is Pam Whitlow.
Right, it's Pam and Jeff Whitlow.
Okay.
Okay,
Thank you.
thanks.
Eric has a question next.
Yes, hi there. So I have a 14-inch Dobsonian that,
Nice.
you know, it's big, it's heavy, it's a pain to carry around and such, but I went ahead and invested because I have so much money invested in this whole astronomy thing. What's an extra $500 for a bino viewer? So I find something like this really helps seeing objects
I would imagine so.
in the city. You know, all the light pollution that we have here. I'm in a Bortle 6. I'm here in Littleton, and
Okay.
so this is an Orion premium. You call it about $500 for this thing, and they also make one that's about $220, and a couple not so fancy eyepieces I find work very well. So this is just an option. If you really want to utilize both eyes, you'll say, yeah, it was worth the money. It really helps a lot. And so our next open house that we have, I will bring these with me with my eyepieces, and anybody wants to just slip them into their telescope and check them out, that's fine. I'll do that next time we have a open house. So anyway, that was it.
Yeah, bino viewers are nice. Every time I see somebody with them, I'm always like, oh, that must be so comfy.
But it's worth it. It really is worth it. It's definitely look into it.
Yeah.
So
I have quite a list of things
Yes.
that I'm looking into to keep trying to get every little edge. So, as I'm sure
Yeah.
most of us do.
this helps a lot. So,
Cool.
all right.
Thank you for that.
Okay.
Yeah.
Yep.
I saw Ron's hand earlier. Ron, do you have a question?
Eric pretty much tackled it. I was going to ask Sean if he had tried a bino viewer. I've used a bino viewer in the past, and while it doesn't make a true binocular scope out of what you're looking through, and you think, well, wait a minute, if I'm putting the bino viewer where the eyepiece goes, I'm splitting the light two ways, so technically I'm cutting the light in half, going to each eye. But the brain does this really nice job of integrating the images from the two eyepieces, and you actually see, I've heard as much as about a 40% improvement in detail in the images. And I've got to think that that using a bino viewer to try to find a few dim objects might be helpful too, because you're taking advantage of looking with both eyes. The downside, of course, is for the bino viewer, you need two of each eyepiece.
Yeah. I think I'd be hard pressed to convince my wife to let me buy two of all my nice Explore Scientific eyepieces.
Well, what you do is pick out, say, a couple focal lengths, a short focal length and a long focal length, or maybe a short and a medium focal length, and just get a couple pairs of eyepieces and use them that way. Because otherwise, you go broke trying to buy pairs of every eyepiece that you want.
Right.
Okay, Eric, do you have a comment, or you just forgot?
No, I'm just looking at my eyepieces I have. So I just have two sets. Again, this is a 14.5, two of those. And whatever these are again. Let's see, these are 27 millimeters. And these are the Orions. These are about maybe $150 each, maybe-ish. So it's a small investment, but I think the return is well worth it.
Yeah.
And that's all I have is just two sets. I don't really need anything else.
Okay. Any other questions? I have several comments here thanking you, Sean, finding the presentation very useful from several people. And it looks like several people are asking for the copy of the presentation.
Yeah, we'll have to make sure that gets out.
Right. Incidentally, this will be available on the YouTube channel, so you could easily watch it again. Okay, I have some additional messages here. Okay, so any other last-minute questions?
I have a question.
Yep.
Hi.
Hi.
Can you, I'm so sorry to everybody. Can you explain how you got the formula?
All right. So, like I said, it was the article that I read where a guy said that he just multiplied the magnitude by the surface brightness, and he started with there, and I would like that clicked on in my head, because I automatically went to doing the square root. Since that first part comes from, that's actually a harmonic mean, right? We use the square root. If we had three objects, it would be a cube root. Since the surface brightness depends on the magnitude, right? Like they're connected values. You don't get to one without the other, right? So you wouldn't do the like add and divide. And so like as soon as he said like multiplying worked better, like that's where I started with that, and that seemed to work pretty well. And then I saw that, I was playing with the Messier catalog and was like, all right, we're obviously missing a term, and it's got to come down to the sky quality. And that's where, doing some research, I found that SQM plus 3 part, and I was like, cool, now we have like a contrast ratio. And like just conceptualizing it, I was like, okay, now we need to somehow come up with a way, because I had already observed that sometimes the surface brightness mattered more, and so I knew right away I had to come up with a way to like weight it. And as I looked at stuff, it was like, well, it comes down to the size of the object. So if I had two objects that were the same magnitude, but one was bigger than the other, well, then the surface brightness definitely mattered more on whether or not I was going to see it. And so having already looked up the formula to get surface brightness from magnitude and area, but trying to keep the number of like terms you're adding to it. Like I wanted to just look up magnitude and surface brightness and go. And rather than be like, okay, now what's the area of the object as well? So that's where that came in. And then it definitely seemed to thinking like, well, now we're getting kind of back into thinking about the units that are in there. We're back into using that 2.5 times the log, because that comes from a bunch of stuff. The difference in magnitude between like a magnitude 1 and a magnitude 2 is about 2.5 times. The magnitude 1's 2.5 times brighter. And then the whole thing's a log system. So threw that in there, and I swear it just worked perfectly.
That makes so much sense. Thank you.
Yeah. So
I have a comment. I am not able to, I've had my hand up, but I don't think you're seeing it.
Go ahead, Digby.
yep.
First of all, very useful and good talk.
Thank you.
Let me just offer something as in the way of a comment from somebody with a medical background. World War II fighter pilots used to take bilberries, which grew in abundance in the United K. Very, very hard to find bilberries at any of the grocery stores here, but you can find bilberry extract. And taking that extract for several days before you're going to plan to observe, and this is strictly anecdotal, may help your visual acuity. The other thing that I find helps my eyes in my 8th decade is to supplement lutein and xanthine. There's some good science behind this. So for seniors out there that are conscious of taking care of their eyesight, those would be 2 things to think about.
Okay, that's very useful. There are quite a few seniors here. Maybe you should put that in the chat, Digby.
I can't chat on my phone, unfortunately, Mehmet.
Oh,
It doesn't
yeah,
allow
that's
me.
right. That's right.
It
Okay.
doesn't allow me.
Okay. Okay. Any other comments, suggestions, questions? If you cannot raise your hand, you can always start talking, unmute.
Yeah, Jack here. I just
Yes.
posted a comment, a very excellent presentation of this subject, having been involved in stray light analysis on all manners of things way back when. Again, both thumbs up.
Okay,
Thank
thank you,
you.
Jack. Maybe I have another one here, Sarah, saying she also finds it very, very useful. So another comment. Okay, there are several comments here. They're all indicating that this is a great presentation, Sean.
Appreciate it.
Thank you for the talk and very informative. I'm just reading the comments for you. So thank you very much. This is a great presentation, very useful. And what I will do is, number one, this is going to be available on our YouTube channel, so people can watch it and recommend to other people. That's number one. Number two, if you want a copy of the charts, PowerPoint charts, do send me an email. Actually, you can probably send it to just president at Dina's email, president at denverastro.org. And I will forward his presentation to you guys. Okay. Any last minute?
I see Carl asking if we could do an
Yes.
urban viewing part 2, more ideas.
Yes, I see that too. Any volunteers to do it?
If I have more ideas, I'll put it together.
Okay.
I work more stuff out.
But there may be other, Sean, there may be other urban observers.
Yeah.
So that might be a maybe a challenge for others to put together ideas as well, or presentation as well. Since quite a big percentage of our members are in urban or suburban environment, this type of techniques are very useful for lots of people, lots of members. Another comment here from Pam. It says, thank you everyone. Great talk for newbie to learn, especially for those of us who live in the middle downtown in the light pollution. As I said, there are quite a few people in the light pollution areas. Well, thank you very much. Oh, there is a
Comment. Hello. Where's my name?
Jack, you have a comment?
Yeah, I do. There's been some traffic on the LA astronomy bunch of some guys that are doing some serious, very good, excellent astrophotography from Portal 8 and worse skies, and have have sent some of this out. I'll see if I can figure out to copy it to our forums, and I will do that.
Okay.
It's visual. I mean, it's visual photographic work that these guys are doing, not visual, but I still brought up some very interesting comments about how to deal with Portal 9 skies.
I would think
whatever
that
it's used.
I would think that photography would be even more difficult, more challenging.
It would be, yeah. I think a lot of it has to do with narrow band image, narrow band filters can help a long way on kinds of objects, emission in nebulae that have a line spectrum.
Okay,
Yeah, if it's oh, go ahead. I'm done.
I was going to say, I see Pam hand as well.
It's my husband again.
I have a quick question for Sean, and this may be way out in the middle of left field, which I usually am. Does anybody make a light deadening device like the sound filters for headphones? Can you put a exact opposite wave of the noise and cancel light?
I'd imagine that would be difficult because you'd have to somehow separate out specifically like what you're doing. So like you'd have to know that what's coming, be able to separate the light from the object that you want to see from the noise light of the sky glow or local lights and things like that. And that's kind of what, the various filters are attempting pretty much.
And my brain just went to, if you took a general portion of the sky that was quote dark or light to you, use that as your filter and inverted it. Could you is this, am I way out left field, or is this something I should ride around in my brain for a while?
I mean, if it would be done, it would have to, I assume it would be night specific, location specific, where I mean they make those electronically assisted viewing, essentially night vision eyepieces.
That's kind of
in theory, I could see it being possible that if you gave it essentially like a noise, and this is where the musician and audio engineers coming in, if you gave it like a specific noise gate early on, you'd probably still lose some of the stars. It might not work on galaxies as well, but it would be a cool effort.
Okay, I'll put it in my project list and let you know if I make any progress. How about that?
Yeah.
Good.
I am all for people tinkering on weird things that sound out of left field, because that's where cool stuff comes from.
Okay. There is a comment about narrow bands. Somebody is asking. Oh, Sarah. Narrow bands, what's the question exactly? Okay. I don't see any more.
I think that narrow band comment was out of me and from
Yeah, talking about the astrophotography in LA.
Oh, I
Yeah.
see. Okay, okay.
light bulbs.
Okay, well, thank you very much for attending. Thank you very much for the presentation, Sean. I think from the Q&A, you can tell that your presentation definitely triggered lots of interest and lots of comments and questions. So it was a great presentation and great delivery. Thank you
Hopefully
very
it
much.
inspired a lot of people to set up next clear night we have. Thank you
Yes.
everybody for coming. I really appreciate it.
So